made fun of John.
Thanks for noticing. That's actually why I was out on Friday, because I usually make my hair points like a month in advance, and it takes me all day to have my stylist do my work. No, actually, I was in the building. I was doing some guest lectures in some other classes, in the TOK classes. See? Yeah, nothing happens unless it gets tweeted about, you know. So. Okay, anything else that we need to address besides questions that have come up over the last couple days, or my haircut? Yes, Brandon, I'm worried. Yeah, you need to come up with a maybe up to one page here, kind of feasibility study of some kind. Kind of give me convince me that, tell me what you want to do, but also like convince me that it will actually work and like will be a good exploration somehow. Yeah.
After like give our topic proposal on our next Monday, can we like change our project if we find something like
you could. I mean, I think that would be for your own sake. I think that wouldn't be desirable, just because you want to have get a foot into this here, start going, and but if need be, that would be okay. Hopefully you can iron out those details between now and then, rather than after that. All right. Well, let's turn our attention to our first notion of vector multiplication. I hesitate to say that, because there will be two ways in which we define kind of this idea of vector multiplication, which is why we kind of stopped short of saying anything about that the other day when we were talking about different operations that we can do with vectors. We stopped short of like defining one of these products. And it's important that we always say like the dot product rather than like just product or multiplication, because this product we'll also define another kind of product. So it will be confusing. You need to be able to say dot product. So I think for the most part it happens in the way you might expect, except that notice that you're doing u1 times v1 and u2 times v2, and then you're adding them together, which means the result of dotting two vectors is what? What do you get as a final answer? Yeah, a scalar is actually what you'll get in the end, won't you? You get two vectors, you dot them, and the result of having done that is some scalar, some one single number. And it still remains to be seen whether this is a useful thing to do, but you can trust me at least right now that that's a good way to define it. Let's go through and prove each of the following properties, at least in our heads. The first one follows immediately from the real numbers commutativity of real numbers. So u dot v equals v dot u. Why? Well, because isn't it true that what would v dot u be? Wouldn't it be v1 u1 plus v2 u2? Well, that's the same thing as what we have up here. If you take real numbers and be commutative, that immediately implies that vector, the dot product, is commutative if real number is commutative. Check the second one. Does that make sense? If you dot a vector with itself, then you get the magnitude of that vector squared. Try it. What would u dot u be? u1 u1 plus u2 u2. Is that the magnitude of u squared? It would be u1 squared plus u2 squared. Yeah, that's if you were to take the square root, that'd be the magnitude. This one's not worth mentioning at all, probably, but there it is. The zero vector dotted with any vector gives the number 0, the scalar number 0. This fourth one you might think of as kind of a distributive law for the dot product. And then the last one you might kind of think of as the associative law for the dot product. But it's a little weird because by C here, this is not a typo with the font. That C here, I know I should have said this, but let that non-bold C be some scalar number. And just notice that can go anywhere you like. The thing that doesn't make sense to even ask about is like u dot v dot w. Does not make sense at all. Like, doesn't even make sense to ask that question, right? Where u, v, and w are all vectors. So if you were to resolve one of those dot products, you'd get something that was a scalar, and that can't be dotted with a vector. You know what I mean? Yeah, okay. So but you have at least some semblance of an associative property in this last property number 5. So I'll leave those last two for you to prove. They might be hard to say out loud, but you can prove them pretty quickly. And then just prove to us that you can actually take a dot product and that you understand this whole IJ thing too. And just turn to your neighbor, you can even do this in your head probably, and tell them what dot product you get. Remember the answer you're giving them is a single number. Give you a chance to catch up for a second. Yes? Dot product, what did you get, everyone? Anyone? 27, yes, good, good. How do you get that? Oh yeah, that's right. 3 plus 24. Okay, so you just multiply the x components and the y components and add those. Okay. So the very first nice application that we can, where the dot product appears in a formula here, is in this formula right here that we're about to show you. The angle between two vectors is given by this formula. And on a day that isn't a half day, I might prove this for you too over on the board or something. But I'll leave the proof to you. It's actually not, I don't know. I think it's doable for you. It's not immediate maybe, but I have this, obviously these two things are exactly the same piece of information, just written in two different ways. So I don't know which form you like better for this formula. I don't know. They're the same formula. You'll just see even later in this lesson that we may prefer this mode later, but they're the same result. So, like I said earlier, someone was asking, what about the notation we use? There are lots of different notations we use for these things, for vectors, right? So let's just show you one more if we haven't seen it already. Columns, like this. You like that? No. That's actually IB's favorite way of writing vectors. So it's worth learning, even though your book doesn't like that way. It's worth noticing and not being scared by it. So that's x component is 4, y component is 5. Just if you want to rewrite it as 4, 5, yeah. If you want to rewrite it as 4, 5 instead of 4, 5, you can. Yeah. Yeah, and so actually, yeah, do you remember when we used this for translations? Yeah, very good. So actually, that's actually the context in which we didn't use the word vector then, but that's actually a translation vector, is what that is. Oh. So that makes sense. That's the exact same context. They mean exactly the same thing. Just at that time when you were introduced to this notation on one day earlier this year, we haven't really emphasized it, but we just didn't want to use the word vector then, because we didn't think you could like emotionally handle it. But there is something else that we will deal with soon that uses this notation, but it'll be so context different than this. It'll be such a different context that it won't matter. Okay, so so are you already trying to do this here? Cosine theta here for these two vectors is, you might need a calculator along the way too, is u dot v, or in our case, r dot s. So let's just do that. What is that, 12 minus the 7 up top? Over the two magnitudes here, the product of the two magnitudes. So what is that going to be? 16 and 25. Is that root 41 for that first magnitude? And that second magnitude is root 10, right? All right, so theta will be equal to the inverse cosine of that. And we'll get an approximate answer since no one knows what angle we're talking about there. I'll have the cosine of 7 over root 4x. $69. 70.0. So 69.8?
Oh yeah.
It's all good. Can you confirm, Grace, or someone else rather than Good. So, yeah, maybe we'll have to come back at some point and hit that with proof to why this works. But angle between, that seems useful, Mr. Chase. Thank you for sharing that with me. Okay.
How do we know we want
yeah, so the angle here is, yeah, the only thing that could be maybe an issue is that, I mean, the whole like quadrant thing, in fact, you'll never want to necessarily report a negative angle. This is like the angle between two vectors. So it's not really like meant to be, like, there's no reason you would give an angle bigger than 180 even, right? You'll always give it an angle between 0 and 180, which is exactly what inverse cosine always gives you, right? Now, there is actually an argument that could be made that someone should give you not this, but this, the supplement of this. Can you think of the, you can imagine that like maybe, I don't know, that you'd be in a situation where someone might say that instead. Just because, you know, they're kind of, or 360 minus this, I guess that's what I meant. Right, because really in between two vectors there are two angles, right? There's this angle, or someone could say, what about that angle, you know? So technically I guess you could give either one of those, but I don't think it makes sense to give like a negative angle or anything like that. This is a fine answer. We should go back to this formula just for a second here. If theta is 90, what do you get for the dot product here? If cosine of 90 is 0, then u dot v will be 0. So that gives you this first result here. Furthermore, if on that last page here, one way we wrote what the dot product was by saying u v cosine theta. When will that be at its biggest value? So cosine, so the dot product will be 0 if they're at 90. If the two vectors are at 90 degrees. You can see that right away. When will the dot product be at its largest value? 0 is when you're at 90 degrees, you're at the smallest it could possibly be. The dot product is 0 at that point. At what angle? You fix the two magnitudes in your mind and just adjust the angle between them. When do you get the largest possible value of those two things? What angle? Which, yeah, 0, right? If at an angle of 0, notice that this is 1. The dot product will always be the product of the two magnitudes times this cosine of the angle between them. So cosine theta gives you some kind of a threshold on how big that will be. If the cosine, if theta is 0, then the dot product goes to 0. Excuse me, if theta is 90, the dot product is 0. But if you're at 0 degrees, then you get the biggest possible thing, which is just the product of the two magnitudes. Or 180, possibly, right? 180 degrees apart, too. So it's worth mentioning, so certainly one way you could like kind of pick up, that you could detect that two vectors are in the same direction, or parallel, or I don't know how you want to say that. One way you could detect that is by doing the angle between formula, like we just did, and see that the answer you get at the end is 0, or 180. Or you could just notice, if they really are in the same direction as one another, that the other way to do it, besides checking the angle using that formula, is just to see that they're scalar multiples of each other, right? Then it should be obvious that they're in the same direction, that the angle between them is 0 or 180, right? So, for example, show that B and C are parallel vectors. That is, they're in the same direction. I don't know. They're scalar multiples of each other. They're parallel. Oh, I'm sorry. We should say what orthogonal means. Orthogonal means perpendicular. Sorry, that's the third. I forget that. You haven't heard that word maybe yet. So, perpendicular. What was the other word we used for perpendicular? The end of last semester. You remember? Yeah, normal and now orthogonal. You got 3 words for perpendicular in math now, and I think we'll never introduce another word for perpendicular again, but you got them now. Okay. Perpendicular, it's such an important idea that it has multiple names that tells you that it's an important idea. Perpendicular, they're actually a little bit different in their meaning, but orthogonal is one of the favorite words that we'll use in like kind of a linear algebra context when we're doing with vectors and matrices and stuff like that. Yeah.
So on like the plane, what would two parallel vectors be?
So they're pointed along the same line. In the
So
plane.
as if in like a coterminal, like when we were.
If you were to extend the ray or something like that, yeah, they're either in the same direction or opposite directions and multiplied by some scale them out. They're scalar multiples of each other. So, in fact, if we think that they're parallel, then we should actually be able to write down what the scalar multiple is. So, in fact, B is what? B is what times C? Yeah, we could just, and that demonstrates right away that these are parallel. And yeah, again, I use the word parallel loosely, but that's what that said to say, so we should be able to demonstrate the scalars that we're actually using to show that they're parallel. And then show that A is perpendicular or orthogonal to both of the others. So how can we check that? Just check that A dot B is equal to 0. Let's just see that that's true. Is that right? Negative 42 and positive 42 is 0. So there we go. And A dot C, is that also 0? 21 and negative 21. Therefore, A is orthogonal to B. A is also orthogonal to C, of course, because they're parallel. So that's what this says up here. Ortho means straight or like at a right angle to something else. And that reminds you maybe of the words like, what else do you hear the word ortho? Yeah, what do orthopedists do? Yeah, no, but they worry about making you straight again, right? Whatever it might be, parts of your body straight again. What else? Yeah, they make sure your teeth are straight, right? Ortho, Steve heard of it?
I did that. I'm so
An orthodox faith of some kind, if you're an orthodox Christian or Jew or something, is one that's straight with respect to the doctrine of that religion or something. Orthodox person or something. Here's something that will not be tested at all, but I think is an interesting, useful, beautiful, cool example of where the dot product comes up again and angle between stuff. This is called the projection of two vectors, and particularly the way you might read this out loud is the projection of U onto V. And that's a good name for it because here's the picture. We're actually thinking about projecting U onto V, like it's almost like the shadow of U on V. So we call that like, you could call it the projection, you could call it like the shadow. Here's another way to maybe think about it too. You can think of it as like the component of U in the V direction, right? Like if V was the new x-axis, if this was your world, if V was the new x-axis, the projection would be kind of like your new x component, right? If that makes sense. And the way to calculate that, if you wanted to derive that formula yourself, you might think, okay, well the projection is going to be just the vector V, isn't it? But rescaled by a certain amount, isn't it? Do you see that in the end the projection comes out to be a vector quantity? Sure you do. What's in the parentheses? U dot V, that's a scalar. Magnitude squared, that's a scalar. So everything in the parentheses is a scalar. And then we're multiplying that by V. So notice that the projection ends up being just another vector that's in the direction of V, which is exactly what we desire, isn't it? Isn't that in green what we're trying to show? Now, of course, the trick will be figuring out what the appropriate new magnitude should be. But that's not too bad. If you know the angle here, what would this be here? Well, it would be the magnitude of the projection. The magnitude of the projection should be the magnitude of U times the cosine of the angle between. Do you agree? That would be the magnitude of the green vector. Yes? And by the way, cosine theta is also known as u dot v over the magnitude of u times the magnitude of v. Isn't it? From the previous slides? So if you multiply this by, if you multiply the magnitude of u times the thing on the previous slide, what does that look like? What do you get? You get u dot v over just the magnitude of v, right? Don't they cancel out? So this represents just the magnitude of the green vector. Now, thinking about unit vectors, what's the length of, what's the vector? Can you write down an expression for the unit vector in the direction of v? Sure you can. It's v over magnitude of v. And if you multiply these two things, you get that. Right? If you take the unit vector and then you give it this magnitude instead, you get that. So that's the where this comes from, in case you're wondering where that crazy formula is. So find the projection of this vector onto that vector. So go ahead and, I mean, that was all fun to talk about, but in the end, just run the calculation here. This is the kind of thing, by the way, that you might be interested in. This idea of projection is an important one. If you have one place where vectors turn out to be extremely important is in computer graphics. So anyone who's, in fact, I don't know if you've ever used like Illustrator or Inkscape, or I'm trying to think what are the other ones that are out there. They save their files as something called vector graphics, a vector format for graphics, and that saves instructions for how to redraw the picture so that you can enlarge it as big as you like. Have you ever thought about clip art, like why it never gets blurry, like when you expand it? Have you ever? Isn't that true? Like if you've ever used a piece of clip art, you can make it like infinitely large. It doesn't lose resolution. Those are called vector graphics, and the reason is because what's saved is not a pixel by pixel account of what happened. What's saved is actual instructions for how to draw the picture, right? So anyway, so the point is graphics are usually thought of as vectors. And imagine if you had a 3D world in vectors and you wanted to show it on a 2D monitor. You might want to take all those vectors in all of 3 dimensions and project them onto a 2D plane, right? So this is a very cute little 2-dimensional down to 1-dimensional analog of that problem. But that's a big idea. This is kind of the kind of thing you do a lot. You definitely study more about this if you want to do more with computer graphics or something someday. All right, so what'd you get up top here? What's u dot v is 8 over 13. And then we're multiplying that by 2, negative 3. So we get for the projection, what, something messy. 16 13ths and negative 24 13ths. So that's part of what was asked here. I modeled this problem. It's a little weird maybe in the way it's worded, but I modeled it after the book. So it asks you then also, not just to find the projection, but it also says write u, that is 7, 2, as the sum of 2 orthogonal vectors, one of which is this one. So let's go back to this picture for a second. If one of the vectors is this one, if I add to it another vector that's orthogonal to it, and I get u, the other vector that we're talking about is this one along here. If you want to think of the projection as being kind of the new x component in our new world with respect to v, we're kind of looking for like the y part, you know, the other vector. So I don't know what that is, but I do know that if this plus this equals this, then this is equal to this minus that. So I think I can find that other vector's components. 7, 2 minus this, and whew, fractions. You could do something harder, but anyway. So come up with what that is, please. Someone do the fraction work for us. What is it turn out to be? 75, someone check these. 75 over 13 and What's the other one? 50 over 13? Someone check that. So I think we've done it then. We found this is the sum of two vectors that equals 7, 2, that are orthogonal, one of which is the projection. So that's a little weird, but they just have some questions like that on the homework side. There's one more thing I need to like kind of shout at you as we go, because the bell's going to ring in about a minute. And that's at least to give you, even if we can't get through this last example problem, the formula for work. So this is like a physics idea, right? You've probably heard of work before. But the work is a scalar quantity, and it's equal to the dot product of these two vector quantities, force and displacement. So the way that you'll often want to compute it, if you have the two component forms for those things, you just dot them to get work. More often than not, you may have, not that information though, you may have the magnitude of the force and the magnitude of the displacement, and you'll have the angle between those. So those are both good ways to calculate it. The idea here is pretty clear, maybe, I think, right? How much work is done if I pull the chair at an angle like this? Well, it moved 3 feet, and I applied, whatever, 20 newtons at a certain angle. But was all of my force in the direction of the work that happened? No. Only a portion of it was. How much? The magnitude of my force times the cosine of the angle, right? You break that force I have into two components. We'll talk more tomorrow. Never mind. All right. But I think that formula will get you through those work problems at least. We can try a few tomorrow. All right. Thank you for putting up with a very tight, quick class today. We'll try to go over some homework questions tomorrow. Homeworks 1, 2, and 3. I'll check them all tomorrow.